Hello everyone, welcome to this video. Today I will describe about the basic principle of automatic voltage regulator. I hope it will help you a lot. Please stay along with this video. Here is the circuit diagram of AVR. AVR means automatic voltage regulator. So basically in AVR there are two parts. Number one, how AVR itself works. Number two, how AVR control the excitation of the windings. So in this diagram you can see this is AVR, automatic voltage regulator. So first we will describe the how AVR itself work. Then we will describe how AVR control the excitation of the generator. All of we know that when there is a change in load, that time AVR control the voltage of the generator. Then how it controls, then we will describe in the video. First we need to familiarize with the diagram. This is alternator stator windings. From this line is going to the bus bar, output to switch port. Then this is step down transformer, 440 voltage to 10 voltage AC. This is bridge rectifier which converts AC signal into DC. This is voltage comparator, this which is consist of Zener diode and resistor. Then this is amplifier which amplify the error signal, and this is SCR, that means silicon controlled rectifier. And after that this is the exciter field windings. This is exciter rotor 3-phase windings, and after that this is rotating the diode and rotor windings. Those whole things are rotating, and this is stationary, and this is also stationary. So now we will describe the basic operation of AVR. This transformer is step down transformer. So we know the principle of step down transformer. Here it is constructed in such a way that the output will be 10 voltage AC, and this bridge rectifier will convert this 10 voltage AC to 10 voltage DC. So how it works? This bridge rectifier works in such a way that the output end of this will always be positive. So how it will works? Now question may arise. Whenever this end is positive, that time this flows this way. From this point it cannot go this, it flows this way, and from this point it cannot go this, it flows this way. Then after this voltage comparator it flows again, and from this point it flows to this point. Now question may arise, why it cannot go upward? The main point is that this electricity flows from higher potential to lower potential. In this point this is higher potential and this point is lower potential compared to this. So is as a natural it will flow from this point to this point. So why at this point voltage drop is more? Because this current flowing from whole circuit, there will be a voltage drop. So electricity will flow from this point to this point and circuit is complete. But if it is negative terminal, if you consider this is negative terminal, that time the flow will be in the same way. That means this end will be always positive. Now you can ask it how it may happen. If this is positive and this is negative, that time the flow is in this path to here to this path. Now this time it will not flow this way, because in this case this point is higher point and this point is lower potential point. So electricity will flow from higher potential point to lower potential point. In this case this is higher potential point, this is lower potential point. So electricity will flow from this point to this point. That means circuit will like that, from this point coming and through this, from this point coming and from this, circuit is complete. So this is the capacitor, which is known as smooth running capacitor. As usual, it is used to reduce voltage surge, and normally capacitor filter out the AC noise in the circuit. The most critical part in this diagram is in the use of Zener diode in voltage comparator. How Zener diode works here? This Zener diode is specified for 5 voltage. So whenever here is 10 voltage DC, that time 5 voltage can pass through this and other 5 voltage can pass through the resistor. If the voltage is less than 5 voltage, that time there will no flow inside the Zener diode. Whenever the voltage is more than 5 voltage, that time there will be a flow. So when it is 10 voltage, 5 voltage is passing through the Zener diode, 5 voltage passing through the resistor, and you see this is after the Zener diode, voltage drop will be 5, and after the resistor voltage drop will be 5. That means there will be no difference. If there will no difference, that time there will be no error signal to the amplifier and there will be no excitation. So whenever there is a change in voltage, that means if we are not getting 10 voltage, if we get 9 voltage, that means whenever we are getting 9 voltage means there is a change in load. That means due to change in load, our voltage drops. So our voltage drops in 9 voltage. So 5 voltage will pass through the Zener diode and 4 voltage will pass through the resistor. So there will be a voltage difference, +1. +1 means we need to increase the excitation. So this +1 signal will pass through the amplifier, which will amplify the error signal. The main function of the amplifier is to amplify the error signal to the SCS circuit. Here excitation control using SCR trigger control. So after the amplifier, this signal coming to the SCR. that means silicon control rectifier. Now how it works, we can see that there is this two diagonal is connected to the AC signal and two diagonal is connected for exciter field windings. So this is one type of thyristor. This converts AC signal into DC signal. So whenever AC signal coming from this side, if it is positive, then the flow will be from here to here. If this is positive, then flow will be from here to here, and the circuit is complete. This similarly like this bridge rectifier. The function or working principle is same, but there is a difference. Whenever we need to excitation according to our load change, this input signal is AC, but the output is DC. But in this case, we will not use, or we do not need this full DC voltage. So what we need? We need how many DC voltage we need. This will control this SCR trigger unit. So from the signal, error signal from the amplifier, output error signal control the firing angle of thyristor or SCR through a triggering circuit. That means how much voltage we need to excitation, that will control this triggering circuit. How it controls? So assume this is the voltage, DC voltage. So at which angle its SCR is triggered? SCR is triggered is known as firing angle. At which angle its SCR is triggered is known as firing angle. And after this is this voltage, we will only use this voltage for the excitation, and this side voltage we will not use, because this is before fire. This is the firing angle. This alpha is expressed as firing angle, and this cross section area we will not get for the excitation. We will get only this area for the excitation of these windings. So you can get easily this how much voltage we need will pass through this. This is DC voltage and causes the excitation. And this way, whenever this causes the excitation, that time it will control the generator voltage. Now how it will control, we need to understand this. So here, before we describe this AVR, how AVR controls. Now we will see how AVR manages the excitation of the generator. Here see, this from AVR signal is coming to the stator. That means DC voltage is coming to the stator, and due to DC voltage coming to the stator, you can see here this parts is rotating. This full, this is shaft, this is engine side, this is main AC exciter, this is stationary part, this is rotating parts. This is rectifier, this is main rotor, this is main stator, and three-phase supply is drawn from the stator. So AVR control the excitation in the stator windings. As there is a DC voltage in the exciter field windings, and this rotor is rotating, that's why AC current is induced in the rotor windings. Again I am telling, as DC voltage is applied here and rotor is rotating, this part is rotating, that's why AC current is induced in the rotor windings. AC current will induced in the exciter rotor 3-phase windings. So this AC current will lead to this rectifier, that means rotating diode. This AC current will lead to the rotating diodes, and this will convert AC to DC, and this DC current will supply to the main rotor windings. See, exciter rotor 3-phase windings to rotating diodes. After rotating diodes, it comes to the main rotor windings. So this is how it controls the excitation. So whenever there is a more current in the rotor windings, that means more magnetic flux cutting and more voltage produced. So whenever there is a increase in load, initially increase in load, that time there is a drop in voltage. So whenever there is a drop in voltage, we need to increase the voltage. That's why AVR gives the signal or gives the voltage to the stator windings, and there is a induced current in the rotor windings. So this induced current will pass through the rectifier, and rectifier converts this current AC to DC, and this DC current will supply to the main rotor windings. And as there is more current in the main rotor windings, that means more magnetic flux will cut and more voltage will produce, and you can this voltage from the 3-phase windings. So this is the main basic principle of the AVR. So in short, again I am telling you in a summary. This is AVR, how itself work. This is how AVR controls. Now we will go to the how AVR itself work. This is step down transformer. This AC signal come to this DC, and after that this voltage comparator. Whenever there is change in drop in voltage from 10 voltage to 9 voltage, that means we need to increase the excitation, we need to increase the voltage. So signal coming to the +1 error signal, amplifier amplify this error signal through the SCR trigger unit. SCR trigger unit controls how much voltage we need. We don't need this full voltage, we don't need this full voltage, we need how much voltage we need. This will control the SCR trigger unit will decide how much voltage we need. This portion we will need, and at which angle SCR triggered is known as firing angle. Before firing angle, this portion we do not need, this is off portion. After firing angle, this is known as angle of conduction. This portion we need. So how much voltage we need? According to this, there will be a voltage available in the exciter field windings. As voltage available in the exciter field windings, then there will be induced current in the rotor windings. Induced current in the rotor windings, which is 3-phase windings, and this AC current will pass through the rotating diodes, which converts AC to DC, and this current supply to rotor windings, main rotor windings, and there will be more magnetic flux cutting in the stator windings, which is also three-phase supply. So in this way, the required voltage will be found at the stator windings, and this from stator windings, this supply is drawn to the bus bar or the output to the main switchboard. I hope all of you understand this video, as it is a very long video. Some of you may get bothered, but I hope all of you understand, as it is also interesting also. So thank you very much for watching this video.